Hi friends, welcome to this channel. So in this video, we are going to look at problem 2385, amount of time for binary tree to be infected. In this video, we are going to solve this problem by reviewing this problem as a general graph problem. So as you can see from the coding, so this viewpoint is crucial for solving this problem. So meanwhile, this problem is also the daily challenge problem for today. So our plan will be the following. First, we're going to digest the problem requirement, and then we do a simple analysis, and finally we share the code and make some comments. First, let's look at the problem digest. So here we are given a binary tree with unique values. So this is actually a very important assumption. And also we are given an integer called start. So at minute 0, an infection starts from the node with value start. So we can identify this node because the values are unique, right? So each minute, a node becomes infected if it's next to a infected one, right? So we want to find the number of minutes needed for the entire tree to be infected. So here we have two examples. The second example is a trivial case, right? So let's look at the first one. In the first one, so we notice that at node 3, right? So this is the original one. So you have this is the infected. So at minute 1, so we get 1, 10, 6 to infected. And at minute 2, we get 5 infected. At minute 3, we get node 4 infected. At minute 4, we get 9 and 2 infected. So this way, actually, also from the analysis, we see that we can regard this node 3 as a source, and then we got infections layer by layer, right? So this is actually is nothing but the breadth-first traversal, right? So each layer, we are going to increase the minutes. So here, for example, at 3 minutes is 0. And then another layer, so 1, 10, 6, the minute is 1. And at minute 2, 5, right? And the next layer, 4, right? So the next layer, 9 and 2, right? So and then our plan will be the following. Basically, we build a general graph from the binary tree, and then do breadth-first based traversal. So before we do that, let's also look at the constraints. So these constraints actually can be important regarding to what kind of algorithms we adopt or we use. So here, the number of nodes in the tree is given in this closed interval. So it's 1 and 10 to the power 5, right? So node value is in between 1 and 10 to the power 5, and each node has a unique value. So this is a very key assumption for this problem. And a node with a value of start exists in the tree. So this one is basically a consistency assumption. So with that said, we are ready to basically do the code. Here, actually, we are going to use two traversals, right? So in the first traversal, we are going to traverse the binary tree to build a graph. And then in the second traversal, we're going to traverse the graph to get the desired minutes that on which the whole tree is infected. So without further ado, let's look at the coding. So in order to make the code modularized, I'm going to first write a function. So I'm going to call it build graph, right? So we are going to start from a binary tree, and then we are going to get a dictionary. The dictionary is essentially a representation of the adjacency list, representation of a graph. So here I'm going to call this graph dictionary, default dictionary. So each node, we're going to have several neighbors. We're going to use set to represent the neighbors. So here you can write like this, or because the empty set will be just the initial value for this container. Or you can do a lambda, right? You map everything to an empty set, right? This is slightly different. But here, what you pass is a callable. So with that said, let's traverse the binary tree. So here you can use whatever traversal algorithm you would like to. So here I'm going to use depth first based traversal. So here we have a root. So basically you can add one in order to make it complete. For example, if a null tree, right, which just return a null graph. So let me add this one. If not root, we're going to return the current state of the graph. So otherwise, let's initialize a stack, right? So here S represents a stack, returns the root node, storing the root node, and then it's a basic, very routine while loop, right? So first I'm going to get the node as S pop, right? Then what we are going to do, we're going to check if node left, right? Then we're going to get an edge between node left and node. But notice that the node's values are unique in this problem. So in the graph, we just need to use the value to represent the node, right? So this saves a lot of space, right? So now what we are going to do is graph node value. I'm going to add, because this value, this object graph node value is a set, right? So we can add node left value. But here the graph is undirected or bidirectional, so we also need to do this. Graph node left value. So node value. In other words, node and the node left is mutual neighbors, right? So after we do this, we get the edge. Then we do S append. So we add node left to the stack. So we can do the same thing for node right. Let me add that. So let's change this left to be right. So here actually I first checked the left subtree and then right subtree. So here the order is not essential, right? Anyway, we just finished the traversal. So as this procedure is done, so we finish the build of the graph. We just need to return the current state of the graph. So before we do traversal again, let's print out this graph. So let's call build graph, right? Let's go root. So let's run this to test. Here, let's see, none is not valid type. So here, if not root, we're going to return graph. Yes. So here we have root. Yeah. So test. Well, let's see the test case. Oh, I see. So here we get this case. But in this case, I just need to return a dictionary with key 1. Set 1. There's no edge, right? So now let's look at this one. So you can see 1 has neighbor 5, 3. So we have neighbor 5, 3. And 5 have neighbors 1, 4. And 3 have neighbors 1, 10, 6, right? 10 has neighbor 3. 6 has neighbor 3. And 4 has neighbor 5, 9, 2. And 9 has neighbor 4. And 2 has neighbor 4. This is right? So notice that in this implementation, if there's no edge or just a single node like this one, because here we get this, but we didn't enter the two ifs, we just return the empty graph. So with that said, let's first get the graph. So let's see, build graph. So the root. And then we know we can do traversals using this 3 as source. So let me first initialize a result. The result will be the minute we're going to have, right? So we get 0. And the source will be nothing but start, right? Start. At start, the time is 0. So you can see minutes is 0. And also we initialize a queue. So here I'm going to use collections deck. As deck is bidirectional, but I just want to use the queue behavior of this container. So then we have a list, and we put the source as an element for now. And then we have this one result. So we have sort. Okay, so also we need to avoid repetition, so we use an auxiliary set called visited. So with that preparation, we're going to do the standard while loop. While the queue is not empty, so we first get the node at the minutes, right? So we're going to get queue pop left. Then what we are going to do, we are going to see result equals max result and minutes, right? So actually we just need to check this relation if the node is a leaf, in fact. But if you do this check, it does not change the time complexity. Let's do this just to make it a little bit lazy, right? So also because in the graph, what we stored is actually the value, right? So now with that done, let's check the neighbors. If node not in visited. So here I check this, but you can directly add, but this is for double safe. So we can add visited, add this node, right? So notice that in the queue, although I use node, this is actually a value. I use a value to represent the node, right? So now I want to check the neighbor. For neighbor in graph node, right? If node not in visited. So this one actually is essential, right? So here, we check this and we check this again. But this two checks, though it seems redundant, but it makes it double safe. So here I append this one, right? Append neighbor. So the neighbor will be infected at minutes +1, right? So after this while loop, so we can just return the state of the result variable. So this is the whole logic, right? So before we move forward, let's do a test. Invalid syntax for neighbor in graph node. Let's see. For neighbor in graph node. Node minutes for neighbor, not for, this is the in, right? Visited. This looks better. Now let's see. Yeah, it passes one example. Now let's look at the second one. It should be right? So you have 1, and also you start from 1, right? Yeah, you get 0. Now let's look at the generic case. Yeah, it passes all the cases. So here, before we end this video, first let's make a comment. So here we solve this problem not reviewing it as a tree, but we view it as a general graph. This viewpoint makes solving this problem rather straightforward. That's the one thing. Another thing is that in the graph, so what we build in this specific problem, it's a bidirectional graph, or we can call it undirected. So that's the one thing. And in this build graph stage, so you can use whatever traversal algorithms you like, right? That does not change the nature. And here also we use but first search based traversal. So this is important because we layer expansion to the outside, and then we get the minutes. So with that said, that's basically about it for this problem. So now you can also solve some of the similar problems. So next I'm going to look at all nodes distance k in binary tree. This will be our next video, right? You are welcome to follow up. So with that said, that's it for this video. Thank you.